Welcome to this video. This is Mark Scythian. The date today is August 9th, 2018. In this video lecture, we are going to cover applied calculus modeling for creating equations from given dynamic systems such as an acceleration model of an automobile. This video lecture will focus on using derivatives and integrals for creating equations off of real-world dynamic systems, which could be automobile acceleration, vehicle and aircraft guidance control, quantifying cells and molecules and feedback rates, nutrition to vitals, input-output, and literally anything in the universe could be understood using calculus, derivatives, and integrals. So the important point to learn in this video is that many people are very good at understanding the rules of calculus in terms of differentiation and integration. They do their homework very well, but where some people struggle is taking real-world systems and then creating an equation from it so that they can find out anything else over the function of time or any other functionality. So a function is some sort of input x to get some sort of output y. So when graphed, the curve should make contact with both the x and the y axis in some form or another, or else it is not a function. You put something else and you can't get something out, that would not be a function. So take something really simple and common that everybody's familiar with, the acceleration of an automobile. In this case, the automobile went from rest to 62 miles per hour in 6 seconds. And so this is a velocity rate of change over the function of time, for which the distance attained is constantly changing throughout time. So it's a changing rate of change. You couldn't just divide out the distance and then divide it by time and get some linear increase in distance over every second, because every second the distance is changing. So it's a changing rate of change. So we have to use applied calculus modeling and put to good use the derivative and the integral. So, of course, this is an acceleration, a change in speed over time. But first we have to understand what velocity is. Velocity is a certain speed in a given direction, which is a distance accomplished over a given amount of time. So this becomes a rate of change, a slope, a y over x. And in this case, velocity would be the first derivative. The derivative is simply the rate of change. And that rate of change could be linear, it could be exponential, it could be power, quadratic, logarithmic, etc. But it is still a rate of change. So we're taking a distance y divided into a time x to get a rate of change. So in this case, it would represent a first derivative over the original function being distance, but then distance over what? Distance over time. So it is a rate of change. That is the first derivative represented by v prime. Now, if we were to take the velocity divided by time, remember velocity is distance divided by time, we're then again dividing it into time again, which then becomes acceleration. So if this was feet distance over time seconds, velocity would be feet per second. But acceleration would be feet per second divided by second. So it becomes feet per second squared. Again, it is another rate of change, but in this case it would be the second derivative represented by v double prime, which is equal to a. So now we understand what a derivative is. It is simply a slope, a rate of change, also known as slope. And in algebra, they represent that by m, but it's usually only for linear functions. It may be quadratic also, but we have to understand that to then take on calculus and use it as an excellent tool to find out the unknown rates of change. So we use the derivative to do that. But in this case, we already have a second derivative established. So all we have to do is understand that there's an average rate of change in terms of acceleration, which does become linear. So the opposite of the derivative. So once you have something understood, you find the opposite. And this really allows you to find out a lot of information that is not known to exact certainty. So the opposite of a derivative is the integral, or if this was a graphed quadratic function, it would be the area under the curve. So what we have to do to find the original function equation of this acceleration, we have to reverse the second derivative of the first derivative, and then first derivative to the original function. So the second derivative would obviously be acceleration. The first would be velocity, and then the original function would obviously be distance. So now you have a distance over a time, and every second that distance is obviously increasing, but it's not staying constant. Whereas the velocity is linear, so it would stay constant, and its change over time is linear. Acceleration, it'd stay constant. But that doesn't really tell us the unknown. We have to start from distance. So we have to go and use a double integral of the acceleration. So in this case, we can just use the algebraic rules for acceleration. The final speed minus the initial speed, the y, delta y, divided into the final time minus the initial time, the delta x. So we get 15.16 feet per second squared acceleration. That would be this acceleration representation of the model here. And of course, if you're using metric system, 3.28 feet to a meter, so 4.62 meters per second squared. So now we have our second derivative, which can allow us to solve so much information now. It's pretty much simplified once we get this value here. But then we have to use the calculus rules for integration to reverse the second derivative to the first derivative, and then the first derivative to the original function. So this would require the modeler to have mastery over the rules of integration. Differentiation and integration. So that's the calculus homework, and you do many, many problems and master all the different mathematical expressions in terms of the rules of differentiation and integration. So that's something you're going to have a prerequisite first, but many people, after they do master the rules, they still struggle with creating an equation out of a real world scenario. And once you understand how to get an equation out of a real world scenario, then you could figure out the unknown of anything. It could be healthcare, it could be guidance systems on airplanes, it could be acceleration, projectiles, it could be statistics in elections, money, investments, anything. You can figure out with a high level of accuracy the unknown based on the known. So anyway, we go back here and we have our second derivative. We're going to use the integral to reverse this into the first derivative. So we take this constant, 15.16 dx, turn this into a fraction for simplicity, and then we just use the rules of integrating. Constants become constants times x. Then we reduce this down into lowest terms, so 379 x over 25. And because we don't have any time limits, it's an indefinite integral. We express it plus a constant. So if we put the time x limits in, final time, upper limit, initial time, lower limit, we can then calculate this integral. And at 6 seconds, we have 90.96 feet per second, so which is pretty much 99.89% accurate. So this would be correct. See, 90.9 or 91 feet per second. We could use those. So that's correct. So that now we converted it from the second derivative to the first derivative velocity. We got the equation here. So whatever time we put in for x, even decimals like 3.856 seconds, we can know the exact velocity of this vehicle using this equation as a definite integral computation over some time. So we might put, we don't even have to use the limits. We can just put in any second between 0 and 6 for x and get the exact velocity y. Next, we want to go back to the original function. So we got to find out the distance. And this is where it turns nonlinear. We can integrate once again, going from the first derivative to the original function. So again, we use the another integration. So this would complete the second integral of the acceleration constant. So again, using the rules of integration, we add a power, x to the 1, x to the 2. So if we were to get the derivative of this, the reverse, we would subtract 1. It would come down, so we have to cancel that 2. We use 1/2. So 1/2 times this fraction, we get 379x squared over 50. And again, if it's indefinite integral, we have to put the c, the plus constant. So now we go to the definite integral, and we enter in 6 seconds for the x as the upper limit, subtracted into 0 for the lower limit. We get 272.88 feet distance accomplished during the 6-second acceleration of the automobile. And just to check it, to make sure, we can use an algebraic physics formula. Delta d is equal to 1/2 at squared. So we put in the acceleration, feet per second squared, times the time squared, divided by 2. We also get 272.88 feet as the distance accomplished for that acceleration over that time limit. So that's correct. So this equation here represents this acceleration. You can combine more and more like or unlike systems with more and more equations, use the rules of differential equations and differentiation and integration until you get a master equation or format, which will then become an algorithm, can be programmed into any equipment to get accurate readings in real time of any system. And again, that could be machinery, that could be engines, aircraft, blood flow, blood chemistry, healthcare, all that equipment. All it is equations, integrals, derivatives, and algorithms programmed in, which now we have a Android, or we have a programmable system, PLCs, that can take all this into software or algorithms or computing machine language. So this is just the basic example of like getting an equation out of an acceleration. So lastly, if we were to ask some good questions, this is the equation representing the given acceleration. So let's say somebody asked, at what time in seconds is this car exactly 50 feet from the start point? Which you really couldn't figure that out right here, especially with the changing rates of change. So you get this equation, the original function representing distance, and that would be your x, your time, and then you would have a y, output distance. So we're already giving a distance. So you simply enter in 50 feet for the y and equate it to the equation, nonlinear equation representing the distance component of the acceleration, which is constantly changing, a changing rate of change. So then all you have to do is use just the basic rules of algebra. And so we would just multiply, try to get rid of this fraction. So multiply both sides by 50. So you get 379x squared is equal to 2500. 50 times 50 is 2500. So then it's just the square root of this fraction here. So at 2.6 seconds, this car will reach exactly 50 feet from the starting point. Now, if we take the first derivative of this equation here and to get velocity, you might not care about acceleration because it's average rate of change. It's a linear function. It's a constant. But you might care about what speed the car is at a given time. So let's say you wanted to know when the car, when as in seconds, at what time in seconds is the car at 30 miles per hour. So here we really can't divide everything out and get an average because it's the changing rate of change. So you get the first derivative right here of the original function distance, and 30 miles per hour is 44 feet per second, because for every 15 miles per hour there's 22 feet per second. So 30 miles per hour is 44 feet per second. So all you have to do is equate the first derivative to 44 feet, which is the y of the first derivative, which is feet traveled in 1 second, or velocity. So this is the velocity equation right here. So you would just equal this first derivative equation to what speed you want to find the exact time. And then it just boils down to 44 times 25 is equal to 379x. And then when we divide it out at exactly 2.9 seconds, 2.9 seconds, you're reaching a speed of 30 miles per hour. So in 1/10 of 1 second, it's shooting up already 4 miles per hour. Which, using common sense, you know that this is a changing rate of change over the function of time. It's not linear there either. So the slope would be linear, but the changing rates of change are going to reflect the original function, the distance, which is not linear, non-linear equation, quadratic actually. And let's say you wanted to know when the car reached 50 miles per hour. So again, you take 50 times 22, divide it into 15. That's 73.33 feet per second. We don't have any record of the speed at 50. And we can't just divide these out and get a linear rate of change, because it's stemming off a distance function, which is not linear. So you use this first derivative equation again, and you equate the y to 73.3 to equal this equation here. And then again, you would just use the basic rules of algebra, and 73.33 times 25 to equal 379x. So when you set it up, you get 73.33 times 25 divided into 379 to equal x. So 4.84 seconds. This is when the car at 4.84 seconds, almost 5, say 4.9, say 4.8, it will 4.84 seconds, it reaches 50 miles per hour. So in 16 100ths, or what would that, 8/50ths, 4 25ths, 1 over 4 25ths, 1 over, so 1/5 of a second, it's going to go from 50 miles per hour to 55. So that tells you right there, this is not linear at all. And you need to use the calculus derivatives and integrals to calculate the correct, absolutely certain rates of change, focusing on, in this case, acceleration, velocity, distance, using differentiation and integration. So I made this video because a lot of you are well seasoned at the rules of differentiation and integration. But when it comes to taking a real world scenario and then creating an equation, even good calculus students sometimes struggle on it. And I'm just saying that find that second derivative, reverse it to first, and then reverse it again to the original function. And then you really get a good mastery over this. And then eventually, when you get into more of the applied calculus modeling, you can create equations on anything, program them into equipment, and you can get absolute certainty rates of change in real time. And then a lot of the unknowns that you were struggling to understand, you can really create many of these derivation equations to create algorithms. And then a lot of the projects or problems you're trying to solve, then become very understandable, and you build up a confidence. So you can build up on this, but my focus on this video was to emphasize using integration and differentiation to create equations from actual dynamic systems. Thanks for watching. The date actually today is August 9th, 2018, and have a great day.